Welcome to GenAI Level Up, the podcast where we decode the future of artificial intelligence one breakthrough at a time.
Whether you're just starting your AI journey or you're a seasoned expert, you've come to the right place. Our mission is to make the complex world of generative AI accessible to everyone, everywhere.
In each episode, we dive deep into the foundational concepts, the latest research, and the transformative applications that are shaping our world. It's time to get smarter, faster. Let's level up together.
Welcome to the Deep Dive. Today we're exploring research tackling, one of the biggest headaches in the LLM world, context length. If you're working with LLMs at scale, you know this pain point all too well. Processing lots of text gets incredibly expensive, computationally speaking. It scales quadratically with the length. Yeah, the ON2 thing isn't just theory, right? It's a real economic barrier. You try to double the context, your GPU costs for self-attention just quadruple. Ouch, we really need a different approach. So our deep dive today looks at a solution from the DeepSeek-OCR team, and it's delightfully counterintuitive. They're using images, the visual modality, as a way to compress text information efficiently, basically turning text back into a picture to save on those precious context tokens. The idea is to see if this context optical compression can drastically cut down the tokens needed, but without losing the actual information.
Exactly. And DeepSeek-OCR is their proof of concept here. The core hypothesis is, can we compress text optically before it even hits the main language model decoder? If so, we potentially sidestep that whole token scaling mess. The system itself has two main parts. There's the DeepEncoder, that's the compression engine, and then there's the decoder, which is a fairly compact model called DeepSeek 3B MoE A570M. The real goal here is figuring out the limits. How much text can you actually cram into just a few vision tokens and still get high accuracy when you decode it?
Okay, let's unpack that idea of vision text compression, because that really is the core insight, the thing that could change the economics of handling context.
It's sort of like a picture is worth 1,000 words, but applied very rigorously to token counts. Think about it. A dense page of text might be, say, 1,200 digital tokens if you feed it straight to an LLM. But if you render that page as an image, maybe, just maybe, you only need 100 vision tokens to represent it.
Wow, a 10x saving, potentially.
That's the goal. And OCR is the perfect test case because it gives you clear metrics. Can the model perfectly reconstruct those original 1,200 words using just those 100 vision tokens? It's a direct measure of compression and decompression quality.
Right. So to make that kind of high ratio compression work, they couldn't just grab any vision transformer off the shelf, I imagine.
No, definitely not. They specifically designed the DeepEncoder to handle really high resolution images like scanned documents while keeping the memory usage low and, crucially, keeping that final vision token count minimal.
And controlling that token count, that sounds like the secret sauce architecturally.
It really is key. So the DeepEncoder connects two main vision components in sequence. First, you've got an 80 million parameter SAM-based component that handles local details using window attention. Think of it like a microscope zooming in on patches of text. Then that feeds into a 300 million parameter CLIP large component, which uses global attention. That's needed to understand the overall layout, the structure of the whole document.
Okay, so local detail, then global structure. Makes sense.
But the really clever bit, the truly novel part, is what sits between them. It's a 16x convolutional compressor.
16 times. So that takes the output from the local attention.
Exactly. It might take, say, 4096 tokens from the SAM component and compress them down to just 256 tokens before they hit that big global attention layer.
Ah, okay. And that's brilliant for memory management because the N in that ON2 calculation for the global attention is suddenly much, much smaller.
Precisely. It makes the memory controllable and drastically cuts the computation on the most expensive part of the vision side.
Okay, but let's play devil's advocate for a second. We're still running a pretty hefty 380 million parameter vision model up front just to encode the image, right? The SAM plus the CLIP, are we genuinely saving compute overall or just shifting a big cost from the text side to the vision side, trading one expensive problem for another?
That's a fair question. It is a trade-off, but it's a calculated one. Remember that ON2 cost in a standard LLM happens again and again, layer after layer, this big vision encoding step. It happens just once, right at the beginning.
Ah, okay. So it's a fixed upfront cost versus a scaling cost.
Exactly. So while the initial encoding isn't cheap, if you're processing thousands of documents or dealing with really long context in a vision language model, The overall computational savings from using compressed representations can far outweigh that fixed encoder cost. It's about optimizing for scale. You're moving the bottleneck.
Got it. That
Yeah.
makes sense. So we understand the architecture, the why. Let's get to the results. Did it actually work? Does the quantitative data back up this whole approach? They tested this on the Fox benchmark, right? Comparing text tokens to vision tokens.
They did. And the findings are really useful, giving some solid guidelines for designing VLMs. They found a sweet spot. At a compression ratio under 10x, think 9x or 10x the model, consistently hit 96% or even higher OCR precision.
96%. That sounds pretty close to perfect reconstruction, almost lossless.
That's the idea. It signifies that the decoded text is virtually identical to the original source text, even after being squeezed through that visual bottleneck.
Can you give us a concrete example of that, like specific token counts?
Sure. They took documents that had between 800 and 900 actual text tokens. They compressed those down into just 100 vision tokens.
Okay, so that's about an 8.5x compression ratio.
Right, and even at that ratio, the model maintained 96.8% precision. So that really highlights the sweet spot they found. Nearly 10x lossless compression seems possible using this optical route.
Okay, that's impressive. But what happens if you push it harder? What if you go beyond that 10x boundary and really try to compress aggressively? Does it just fall apart?
They tested that too. They pushed the compression all the way to 20x. So the original text had 20 times more tokens than the vision tokens used to represent it.
That sounds extreme. What was the accuracy then?
Even under that really lossy condition, the OCR accuracy was still around 60%.
60% at 20x. It's actually still pretty amazing. It means the model is still getting the gist, the main points, from a tiny visual representation.
That's the key takeaway, I think. It shows that even relatively small language models, like their 3 billion parameter MOE decoder, can learn to effectively pull information out of these highly compressed visual formats. It really validates the core idea that almost 10x lossless compression is feasible, and it gives us a target for how we might optimize vision token use in future models.
Okay, so the theory holds up, the benchmarks look good. But how does this translate to the real world? You know, messy documents, different formats. How did DeepSeek-OCR do on something like the Omnidoc bench? Does the compression hold up in practice?
Yeah, that's where it gets really interesting from an efficiency standpoint. In those real-world tasks, DeepSeek-OCR, using just 100 vision tokens per page, actually outperformed established models like GOT-OCR 2.0.
And DOCR 2.0 uses how many tokens?
It needs 256 tokens per page. So DeepSeek-OCR is getting better results using less than half the visual bandwidth.
That's a significant efficiency gain. What about really high-resolution stuff where other models often struggle?
Right, for those super dense documents, they have this Gundam mode, catchy name.
Gundam mode, okay.
Yeah, and even in that mode, where it uses fewer than 800 vision tokens on average, it still outperforms Miner U 2.0.
And Miner U 2.0 needs?
Miner U 2.0 needs almost 7,000 vision tokens per page on average for those complex documents.
Wow, so we're talking roughly a 9x reduction in vision tokens compared to Miner U 2.0 while getting better results.
Exactly. That's not just a small improvement. It's a huge difference in the potential cost of deploying these models for analyzing lots of documents.
I did notice something interesting in the paper. The ideal number of vision tokens wasn't the same for all document types. It seemed to vary.
Yes, and that's a really important practical point. Kind of confirms the whole compression ratio idea in practice. Simpler things like presentation slides, they found only needed about 64 vision tokens for good results. Standard documents like reports or books did well with that optimal 100 tokens we talked about. But for really dense stuff, think complex legal text or newspapers with multiple columns, maybe 4,000 or 5,000 text tokens worth of information, you really needed that higher token count Gundam mode to keep the error rate low.
So the model itself tells you, based on the content density, how much visual information it needs to maintain accuracy. That 10x limit seems like a real physical boundary for high-fidelity stuff.
Pretty much, yeah.
And just touching on the production side, again, the speed they could generate training data with this setup was also quite striking.
It really was. They reported generating 33 million pages of data per day using just 20 GPU nodes. That kind of throughput makes it a serious tool for production, not just a research project. But they didn't just stop at fast text recognition. Because they built this comprehensive training data engine, the model can handle what they call OCR 2.0 data. It goes beyond just reading text.
OCR 2.0. So moving from just transcription to actual understanding of the document structure, even non-text elements.
That's the idea. It's about deep parsing. analyzing the document more like a structured object. So using a single prompt, it can look inside the document. For instance, take a chart in a financial report.
Yeah.
Instead of just reading the caption, the model can actually look at the chart image itself and convert that visual data into a structured format, like an HTML table.
Oh, wow. Okay, that's incredibly useful for any downstream LLM trying to use that data. It gets structured data directly rather than trying to infer it from a description.
Exactly. It massively reduces the risk of the LLM hallucinating or misinterpreting the data from the chart.
Makes sense.
And this deep parsing extends to other areas too. It can recognize complex chemical formulas in scientific papers and output them in SMILES format. That's the standard text representation for molecules.
Useful for scientific R&D.
Definitely. It can also handle simple geometric figures, structuring them. And importantly, because they trained it on such diverse data, 30 million PDF pages, it works for nearly 100 languages, including many less common ones, so it has global potential.
This has been fascinating. It really feels like a practical step towards tackling the context cost problem by, well, looking at it differently literally. What's the main takeaway here on context optical compression?
I think the main thing is that DeepSeek-OCR really validates the whole concept. It shows, with empirical data, that you can achieve a significant compression nearly 10x by representing text visually, trading text tokens for fewer vision tokens. And it gives us practical guidelines for how to optimize token allocation in future VLMs.
And they hinted this could go beyond documents, maybe even apply to conversation histories, using this optical processing for older parts of a dialogue to save tokens.
That's a really intriguing direction. If long context is the future, managing that context efficiently is crucial. And maybe this is the final provocative thought for you to consider. They draw this analogy to human memory.
Oh, how so?
They suggest using this optical compression, maybe even degrading the resolution over time, to manage older context. Think about applying that 10x compression not just to the current input, but progressively to older turns in a conversation. You could render the older dialogue history as images, and then gradually reduce the resolution, making them blurrier, essentially, which naturally reduces the vision token count needed.
So like simulating how our own memory keeps the gist of older events but loses the fine details.
Exactly. This kind of optical decay could be a way to handle theoretically unlimited context without needing infinite compute. The context window wouldn't need to be perfectly sharp all the way back.
Huh. So the most efficient long context system might actually embrace a bit of blurriness for older information, mimicking our own brains. That's just definitely something to think about. Thanks for breaking that down.
My pleasure. It's
Yeah.
exciting stuff.
Indeed. We'll leave you with that thought until our next deep dive.
And that brings us to the end of another deep dive into the world of generative AI.
Thank you for tuning in to GenAI Level Up. If you found this episode valuable, please consider subscribing and leaving a review on your favorite podcast platform. It helps us reach more curious minds like yours.
Join us next time as we continue to explore the cutting edge of artificial intelligence. Until then, keep learning, stay curious, and continue to level up.